everyone. I'm Matt Danford, Associate Editor of Modern Machine Shop Magazine. Welcome to today's webinar, Statistical Process Control in 3 Steps. This presentation will outline a 3-step process that leverages the X-bar and R chart, the histogram chart, and capability indexes to not only observe and control the entire process from start to finish, but also to provide a visual representation of that process's capability to meet customer requirements. Our presenter today is Robert Fruit, who has worked for Mitutoyo America for 25 years and has American Society of Quality Certified Six Sigma Black Belt and Certified Quality Engineer training. For the past 12 years, Mr. Fruit has been teaching Six Sigma techniques for the American Society of Quality, the Chicago chapter. The course has 2 semesters. The first is a classroom setting where all the techniques are covered to make sure students are ready for the second semester. And in the second semester, the students actually go into companies and use Six Sigma techniques to solve major problems. This benefits both the students with real-world experience and the companies who get extra resources to help solve their problems. If anyone has questions during the presentation, please type them into the question pane on your screen. At the end, we'll do our best to get to all of them. Also, keep in mind that this webinar is being recorded and will be available on our website, mmsonline.com. Attendees will also receive a link to the recording and their emails. With all that said, let's get started. Robert, take it away.
Thank you, and I appreciate all of you joining us today. SPC in 3 steps sounds simple, but you'll see there are some details here. One thing you need to keep in mind is SPC starts at the point of manufacture. You have to be making good parts. From there, the floor manager wants to know that the whole process is running at its best capability. And then finally, quality control wants to know that the products they're ready to ship will meet the customer's requirements. By the time you get to the quality control question, it's all statistics. So we start with more or less raw data at the top and work through a greater involvement of statistics and predicting what's going to happen. So as I say, step 1 is collecting data and charting. Step 2, we'll use a histogram and some statistics. And step 3, we'll use the capability indexes and see that we are maintaining our process. I want to start by defining statistical process control. Statistics is a mathematical tool that summarizes the current behavior that is expressed in the numeric terms. And that's getting back to the quality control, which are totally dependent upon the statistics of the collected data. Process is any series of steps that take raw material and transform it into a product or service customers are willing to pay for. Control is the expression of statistical tools to enhance the monitoring process. For manufacturing, some of the SP tools include, on the statistics side, average, standard deviation, correlation coefficient, and a few other basic statistics. Charts, run charts, control charts, histograms, scatter charts. We won't get into all those. The control comes in with control limits on average and range, capability indexes, assignable cause and corrective action. You may not think of them as SPC tools, but they're very important. In the manufacturing process, you're going to start out with someone building a CAD model. That in turn gets turned over to a quality control engineer who identifies the points that are critical to quality, what it takes to make sure the part meets the customer's requirements. Machining is set up, and then a PPAP process or its equivalent needs to be conducted to make sure all the equipment involved in the process are performing the tasks needed for making the product. So up to this point, we haven't done anything serious with SPC. We've been working on making sure the product is ready to be manufactured. So we start with step 1, collecting data. And in particular here, we're going to talk about the pre-control chart and the X-bar R chart. Excuse me. When you manufacture a part and check it's critical to quality measurements, it's important that you collect the data immediately at the point of manufacture. You want to get as physically close to it as possible. You're recording and charting data, and you're going to see that in a minute. And the recording things like assignable cause and corrective action, and the only time you have good understanding of what assignable cause and corrective action should be is at the point of manufacture. A week later, no one remembers. So where do we start? SPC starts by collecting data on features critical to quality at the point of manufacture, like we've been saying. And the pre-control chart is a really good chart for operators. It's easy to see, easy to interpret the data if it's in tolerance. It's not a formal SPC chart, which means some people object to it, but they shouldn't, because this is good for the operator. Use the system that captures the data directly from the gauge, eliminates error-prone nature of hand-recorded data, and you get the graphic results immediately. So this means that you're going to want to have someone's good SPC software, and there are a number of good choices out there. The XBAR chart is really two charts in one. The upper portion, the XBAR chart, is about the average size of the parts you're manufacturing. Are they consistent over a long-running period? The R chart, the range chart, is about the manufacturing process consistency over time. Each subgroup represents a small period in time, and it's about the variation that the machine is experiencing. And you'll notice here at the 11th subgroup, we obviously had something happen, which we'll talk about a little bit about later. But this is needed to validate that the process is stable. This is what the R chart is showing you, stability. And that's important in this, using it for statistical projections. So getting to subgroup 11. In the pre-control chart, which happens to be the one down here in the red, the operator records assignable cause, sudden drop in air pressure. They also recorded that they checked the air gauges, reported the problem to maintenance. Maintenance found a hole in the airline. So now you have a complete record, and you want to know over time, how often did you have problems like this? Why did you have problems like this? Is something rubbing against the air hose causing it to chafe? But it gives you an idea of why you go. And this is why assignable cause and corrective action at the time of manufacture are important. SPC systems provide a record of these things that are going right, the data that's in control and in tolerance, and when things are going wrong, that's the assignable cause and corrective action. Control limits are not tolerance limits. They're based strictly on statistics. In this instance, we have an upper tolerance limit of 1.65 and a lower tolerance limit of 1.35. But the upper control limit is 1.57, and you can see how that's different than the other. And the lower XBAR control limit is 1.43. So that means our control limits are totally inside the tolerance limits. It doesn't have to be this way, but in this instance, the statistics do give us that projection. The upper control limit on the R chart is 0.221, and trust your software to do this for you. Unless you're really into statistics and enjoy the calculation, then have your heart's content. But it's much easier just to let the software tell you what it should be and live with it. Control limits are based on statistics, average and standard deviation. The XBAR chart on average is the part of the same size. That was that earlier part. I'm going to back up here for a minute. That's this part across here. Is the part remain the same size over time? And the R chart is the manufacturing process stable over time. And again, I'm going to back up. And that's the chart down here. And you're looking for consistency here. If this is not consistent, you have a serious problem in your manufacturing process that needs to be addressed. Quality control at time of manufacture. This is really important. People tend to put it off, and it's just not good to put it off. The pre-control chart, as you'll find, works really great for the operator on the floor. It's easy for them to see with it collecting directly into it, and if there are problems, like do they get a lot of things up in the yellow or down in the yellow down here, they can quickly spot things that probably need attention before they get out of where you're making bad parts. The XBAR R chart is a manufacturing process maintaining a consistent average and stability over time. And if you had an XBAR R chart that hugged the center line as well as this one does, and they are hugging the center line here, you should be extremely happy. They're usually not that tight on the center line. Stable process. Manufacturing must have a stable process for the remainder of this discussion. If this R chart isn't consistent over time, there's no predictable predictions you can make about the product you're making. And technically, you want the R chart all in control and the R chart all in control. If you have an occasional point in the X bar chart out of control, you find people don't get too excited about it, particularly if you're making parts that are in tolerance. But if the R chart starts wandering out of control, people want to give that immediate attention because that's about the stability of your manufacturing process. We're going to move on to step 2, where we're now looking at the histogram and statistics. The classic histogram. Histogram is a probability density chart, which may not mean anything to you, but us mathematicians it does. So just live with it. The normal probability of the histogram measures the probability of distribution of manufacturing parts relative to the target and tolerances. We're really talking about this where the data is right on target, and then we can see how the data falls off in the same way the normal probability curve is. You're unlikely to see anything that's perfect on average. Here we talk about how much data is really in the center portion, right here. And when we get out further, we're now well out into the yellow range. And you can see it says we have 95% of our data in this range. And I got ahead of myself. And if we get all the way out to here, we're right at the tolerance limits in this instance. And that says 99.73%. We're going to come back to that in a little while. Since this is someone else's chart, this is where I got that chart from. I'd like to give them credit for their hard work. What's the quality engineer looking for? The quality engineer is not usually the operator on the floor. This is now the next person up who's trying to make sure that the process is behaving as it should. We want to look at the peak area on the histogram, peaks being right in this area right here. We want to compare that to where the normal curve says. Now this normal curve is not based on the tolerance limits and the target, it's based on the data. So it's saying the center of the data is here, even though the peak of the data was over here. And you can see some of this because this one falls off this direction, while this is a steeper curve down here. Chances are very good that this is more like what you would see, where you're going to have some out of tolerance pieces at both ends, and this is probably as best tuned you can make this particular process to fit the tolerance limits. We'll have some examples of histograms where there's no out of tolerance. And here we just come back to the same thing we're talking about. You probably have processes where the requirements are so stiff that you're going to end up with some stuff out of control. In other instances, it's going to be very easy for you to meet the requirements because everything falls well within the target range and the tolerance limits. The histogram is a broad picture of the manufacturing process. Now, I'll back up for a minute. This is a detail look. We're seeing what's happening in every part that's coming through the system. By the time we get to the histogram, we don't know whether this data was first, last, middle. It's just data. It's all been grouped together. And we're really on the next one. When you see a histogram of this shape, you know you're dealing with something that is unilateral. In this case, it was flatness. Flatness can never go below 0. If you could make all 0 flatness, you would be very pleased with yourself. But there's going to be some tail off. So we can still use a normal curve to estimate the tolerances, but we're only going to look at it against the upper end. What's the probability of this side of the tail reaching the tolerance limit on the upper side? Excuse me. Most data will use the normal curve and be some form of this. And then we have, when we're looking at data like this, and this should be an eye-opener. In particular, notice how we've been talking about the peak of the data. Where you would expect the peak to be, there's no data. So this is something you would want to start to investigate, or at least be prepared to start investigating if things don't improve very shortly. And again, we're looking at here the statistics and tolerance. What is the average and what is the target average relative to this is the target and this is the offset from average, average minus tolerance. What is the standard deviation? And then you get your plus or minus 3 standard deviations from the average, and how do these compare back to here? You occasionally want to look at numbers. You don't want to just always look at graphs. Sometimes you'll start looking at numbers and you go, well, this makes no sense. The graph looks different. Maybe you need to do a recalculation. Something has thrown things asunder. Another thing you want to look at, here is the average of the data, and there's the target. So this is the offset from the target, and you look at it relative to this. Now this is very small relative to this number. So this is not a place where you would want to make a change. However, if this was the standard deviation, and this is the distance from the target, that is the case where you want to consider, do I need to recenter this process so it is better control? So standard deviation and the difference between average and target, those are two things you want to keep looking at. And when there's a great disparity, either in this instance, it's great, you don't have to do anything, or in the other instance, you should at least think about adjusting your process. The other thought here is when we're looking at numbers, it's not as easy to interpret as the picture. If I was looking at the raw data on this, I would completely miss the fact, or very likely miss the fact, that there was no data sitting here in the middle. So the picture is more valuable than the data, but the data is important. And again, you want to do a comparison between the tolerance limits and the control limits. And if you can have control limits that are well within the tolerance limits, great. This will not always occur. If we back up here for a minute, this would be an example where the tolerance limits would probably fall more out in this range, even outside the range of your tolerance limits. But it's because you're having problems keeping the process in tight enough control that you're only making good parts. So you do want to look at statistics just to validate what you've seen with the graph, but the graphs tend to give you more information. And we've already talked about that. So now we're going on to step 3, the capability indexes and maintaining the process. And this is in a sense, what you're really trying to do is maintain the process, make sure it's stable over time and continues that way. We're going to use the capability of process, CP, capability of process adjusted for average offset, offset from center, and that is the CPK. So we're going to talk about both these. Probably you have never seen capability index expressed in this fashion, but it really is customer requirements over 99.73 of the manufacturing variance. And you're trying to hit a number. So if you're less than 1, by most people's definition, you're not fully meeting your customer requirements. If you're exactly at 1, you're just meeting the customer requirements. And of course, if it's bigger than 1, then you're exceeding the customer requirements and you're quite happy to ship product. Notice I had a comment down here that instead of 1.0, shown here, a lot of people are now trying to meet 1.33. And you'll see that's a much harder target to meet. For anybody that wants to see the formulas, I wrote them out here. They're just formulas. Again, use your SPC software. It'll do the calculations for you, and you don't have to worry about it. Now, also notice we have a CP CPK and a PP PPK. Not everybody uses the PP PPK. They just call everything this. But it is becoming more common that when you use the standard deviation to fill in this value, use PP PPK. And when you're using the R bar over D2, and if people are confused as to what this is, trust your SPC software to do it for you and ask your supplier if you have questions about what's going on. But this one has a tighter look at what's happening near term than this one because of the difference way R bar and the standard deviation are calculated. And the purpose of this discussion is not to get into the calculations, so we won't do any more there. So I wanted to give you a chance to see what CP is. So a CP of 9.0, that's this top graph right here. And you can see the tails tend to go off, but they haven't really reached close to the bottom yet. And that tells me that if I was doing this level of work, CP90, I should expect about 7,000 defects per million. When I get up to CP 1.00, these things are really coming down tight on this, so almost everything I do is in control. And we've fallen from 7,000 defects per million down to 2,700 defects per million. And for people that are trying to meet 1.33, we can see that most of the tail is now here. They're down to 66 defects per million. Meeting 1.33 is quite good. It usually means you don't have to worry too much about there being defects in your product. Now, how is this different than CPK? Well, here we have a really good CPK of 2.0. It's all here and there's lots of space, so we're just not going to be making any bad parts. But if our center starts to drift off from the target, like over to here, I'm now down to 1.33, which we saw was the 66 defects per million. And we're doing not as good, but pretty good. And then if it shifts more to the right, or to the left, if that matter, it doesn't matter whether it's right or left, we're down to 1.0. So we're now down to 2,700 defects per million here, because more of this tail goes off to the right. And if we're down to 0.9 on the CPK, you can see we're getting a lot of tail out here, and we're down to the 7,000 defects per million. So the reason people use CPK is it not only gets in the correct interpretation of how good the center of your body of the process is, but it also takes into consideration how far have I drifted from my target and the consequences of having drifted from the target. The capability index incorporates everything you've seen up to now. And by this I mean the pre-control chart, the control charts, the histograms. So it has now reduced all of that information to one number. Let's back up here again. We have one number now, 0.9 or 2.5, whatever it turns out to be, that represents everything that's happened in this process up to now. The single number can be interpreted to mean defects per million, which we started talking about, and the capability index is one thing that you can look at quickly, interpret if the manufacturing process is achieving the desired level of performance. This is only true when the control charts are in control. We're now coming back to that stability question in the X bar R chart. And the histogram has a normal probability-like shape, which is the vast majority of the time. And even for things like the one-sided one with flatness, you can still use the normal probability curve, but use it on a unilateral type calculations. And I'm coming back for this particular data, which we'll see a little bit more about. And here is the curve. And the curve is pretty well centered on where the data is, but it tells us while we have a 1.18 CPK, how tight it is this way, once we do the fact that it is drifted away from the center, we only have a 1.05 CPK. So it's CP and CPK. This predicts that we'd have 1,800 defects per million. So you're starting to see that CPK, in summarizing what's going on, is also telling us how much to expect in the case of bad parts in a lot. And you want to think about defects per million in terms of delivering the mail. How many letters to the wrong mailbox are allowed? There was a time, if memory serves me right, because it goes way back, that the post office delivered something like 1 billion pieces of individual pieces of mail per week. I'm pretty sure it was per week. It's possible it was per month, but anyway, don't worry about that detail. So how many millions of pieces of mail going to the wrong mailbox would you tolerate before you'd start complaining to the post office? So defects per million has a very important understanding here. And thinking of it in terms of the mail delivery is a good way to think about it. Because I get asked, people would like to know the ranges of CPK and what do they mean in terms of defects per million. And so you can see common numbers here. The 1.5 CPK is equivalent to what is often called 6 sigma. And you can see we still have 6.8 defects per million. So it's not a perfect, but it gets much better. But that's the relationship. And again, I go back and why CPK, not CP, because CPK tracks the fact that you've gone off center. If I back up to that image, it tracks the fact that our data has moved. The job of a quality year. At the point of manufacture, a quality engineer wants to know the parts are in tolerance. That's our pre-control chart. The pre-control chart is in tolerance, and the control chart is in control. So the control chart is now taking a step back from what you see on the pre-control. The pre-control is really details of what's happening right this minute. The control chart's looking at it over a longer range. Could be over a week, a month, but it's looking at it and is it following a consistent set of behavior. And it also determines that we have a stable process so we can trust things like CPK so that we know that we're getting when you're using one number to interpret the data, you need to know that it's based on good information, and that's what stability gets you. So the manager of the floor shop, he's going to move on to the histogram. Remember how that's even taking a further step back than what was happening at the detail level with the control charts. The histogram is now a generalized look at how the data over that week or month is spread out and how does it fit the tolerances. And they're, again, trying to make sure that they've got the manufacturing process running at its optimum performance. Quality engineers' overall responsibility is currently manufacturers repeating historical behavior of the process established by control limits. Remember, it's stability, and it's in control. And then that shows that the current behavior of the manufacturing process is stable, and it predicts what will be in the future. Getting tongue-tied here, sorry about that. Getting back to that. Now, it says that we're predicting the future. Because we've met the stability requirement, and we have every good reason to believe if it's been stable for the last few weeks, it will continue to be stable into the next week or month. We're now, when we get a CPK of 1.33 or whatever the number is, we're not only saying that's what we just did today, it's saying it's what I expect to do for the next month. I'm going to be able to keep shipping product. Thank you for letting me share this with you today, and we're going to see we're coming into the questions, but I've kind of cheated here. I've actually prepared 2 questions based on things I frequently get asked. One is, how do I improve how does SPC improve a process? So we have our X bar R chart. Our chart is not bad. Sort of typical of what you would see. We're kind of wild on the X bar R chart, and we have some points out of control. Certainly we want to tighten that up. When we look at the histogram, one thing that should jump out of this is something seems to peak here and something seems to peak there. And you go, we shouldn't have 2 peaks, that it should all be 1. Why would the process be split like this? And again, I come back into the histogram looked okay. Everything's great. You're not making any bad parts. But we got these 2 peaks. Well, we know that the data source for this data was 2 machining centers. They are all coming into 1 inspection station. And just as another way of interpreting this, it could instead have been plastic injection molding, where there were two cavities. Subgroup size 5 is immaterial to that question. But we have two of something, in this instance, feeding into the same place. The data is mixed. In the system I used here, every place I have a yellow triangle says something has changed about the traceability. So we had a point change there, they're high. It changed here, and now we're low. It changed here, and we're high. We're low, we're high, we're low, we're high, we're low, we're high. Again, we're low with the data. Back up. And it changed, and we're high, we're low, we're high, we're low. Every time it changes, we seem to jump between the two. If our data had looked something more like this, it would have been better behaved. This would be a very typical X bar R chart for a well-behaved process. Sometimes things are moving around, sometimes they settle down, they move back and forth. Our chart is doing exactly what you expect it to do. So this is quite acceptable data. And I only included it so you had something to compare this to see how this one seems wild compared to what a good chart looks like. And again, I now get back into the fact how the yellow marks in there happen where the data, something in the data changed. We kept track of something here, and we happen to know in this case it's the two machining systems. So when I use this to find what is the data that's strictly from A, all of a sudden we get a X bar R chart that looks like this. Our chart again is still good, but we would have expected that. The R chart was pretty good before. It's a little better now, but it's consistent. So that comes there. I'm going to now move on. When I look at both of these charts, here's machine A and there's machine B, I have 0.558 as an average here. Remember, 0.5 is the target, so I'm running a little high on this one. And I have 0.474 here, and I'm running a little low on this one. So it tells me that if I went to machine A and adjusted the target closer to 5.0, and machine B and adjusted the target closer to 5.0, this it up, that should reduce the distance to these two peaks and possibly make them overlap, and I would get a better performing process in the end. Not all improvements are this easy to find, but frequently if you look at data with a little bit of insight, things just start to talk to you. And I said I had a second question, so while it's your turn to start preparing questions for me, I had one more thing I was going to talk about. What is the perfect size subgroup? There is no perfect size subgroup. Walter Shewhart, who developed the X bar and R charting in the 1920s, established the principles that the subgroup is based on. Within a subgroup represents a short period of time so that it only includes natural machine variation. Natural machine variations, the vibrations, variation means the vibrations and tool shifts not influenced by outside events like temperature due to sunlight, low electrical power in the morning due to other companies powering up, etc. So all these elements have come out of here because we're taking such a short period of time. Oftentimes, somebody who might be using a subgroup size of 4, they'll walk up to a machine and take the parts out of the machine, 1, 2, 3, 4, right in a row. That'll make that subgroup. They'll come back an hour later and take 1, 2, 3, 4 again. That'll be another subgroup. And so they come back hourly and keep doing it. So now what they're doing in an X bar chart is I'm comparing what happened on the first hour, what happened on the second hour, what happened on the third hour, and how did the machine behave. Individual subgroups over time represent the shift in long-term history of the machining system. The shifts between subgroups do pick up the environmental effects not seen in the subgroups. You'll see this most often in plastics. Plastics can be quite variable based on whether or not the sun's out, but you go, but I'm inside an air-conditioned room. Trust me, the sun coming out, the fact that it rained today, a whole host of things can make plastics jump all over the place. This makes the X-bar R chart a laboratory test of the manufacturing process to keep the long-term variation in a machine as close to the short-term variation as possible. This is where your stability, when you get it under great control, is happening. The long period of time variability is consistent with the short-term variability. And that goes back to why Schuhart developed it on the rules of when I take a subgroup, it's to represent a very short period in time, and I only see the natural variability of the machine. General rules. CMM data, vision, form, all these types of things, almost invariably the subgroup size is going to be 1. By the time it gets to a CMM or a vision system for measurement, parts are no longer coming off the system 1, 2, 3, 4 like we talked about earlier. So you're going to use a subgroup size of 1 because the data is more or less random. Incoming inspection. It's hard to imagine there was ever be a variation of having a subgroup size different than 1. And again, this is the same thing. And when you get to incoming inspection, you have lost all time-ordered reference to the data. And so you just use a subgroup size of 1. You'll find this is a little controversial. Some people argue I can't go with a subgroup size smaller than 2. Your software should support a subgroup size of 1. And if someone wants to argue strongly about it, if you have an in-house person that's an expert on the subject or use a consultant, you can always talk to them about it. Typical subgroup sizes are between 1 and 5 in general. When selecting parts from a process, time available to measure the parts determines subgroup size. So in general, a subgroup size of 3 is better than a subgroup size of 2. So if you had to choose between 2 and 3 and you really could support 3, you're going to get a better chart. A subgroup size of 4 is not as great an improvement over subgroup size of 3 as 3 was over 2. And certainly 5 is going to be less of an improvement. So if there's a sweet spot, it's probably around 3. Sometimes it's going to be 2. But one of the things that's going to determine this is operators have to walk up, pick up the subgroups, 1, 2, 3, 4, 5, whatever it is, be able to measure it, do all their other duties, and get back in an hour or whatever your time limit is to repeat the process. So that is going to have a great influence on exactly which of these sizes you actually use. When in doubt, you can use the subgroup size of 1 until you get better information to change. And now I really will work with your questions.
Okay, well, we've been waiting for some questions to come in. It looks like, Bob, you might have done a pretty good job at anticipating what people were going to ask about because we don't have any. But that said, if anyone thinks of any to ask Bob later, just keep in mind that this webinar has been recorded. So it will be on our website, and you'll receive a follow-up link so you can go through again, and any further questions you can reach out to Mitutoyo. With all that said, unless something comes in here within the next few minutes, Bob, thank you for the informative presentation. Thanks to everybody for attending. We hope you found this valuable. Again, you'll get a link with the recording. And on behalf of Modern Machine Shop and Mitutoyo, thanks for everybody and enjoy your day.
Well, I could actually add a couple of comments here.
And we do have a question. All right, here we go.
I am a member of the American Society of Quality out of Milwaukee, Wisconsin. They are a good group to work with. They have free resources. You don't have to become a member, but becoming a member and finding out other quality experts in your area could be a very useful tool for you.
That's a good tip. And as I was kind of wrapping up there, it does look like some people typed some things in here, so we have a couple. The first one, the attendee wants to know, he says, how do you plot a single data point on an XR bar chart for a subgroup size of more than 1? And he's throwing, say a subgroup size of 3. How would you plot a single data point on an XR bar chart?
All right, I'm going to scroll back here, way back here. All right, in this particular instance, we have a subgroup size of 4. And so these 4 points, the average of these 4 points is that point right there. The average of these 4 points is the number right there. So what each of these control chart on the X bar portion of the chart represent is the average of your subgroup size. And that's why it becomes a more condensed form. That's why this could be hourly data, 2 datas per shift, looking at a few weeks or a month worth of data, while here we're looking at everything that's being measured on a continuous basis. The R portion is what is the distance between the highest point and the lowest point here. So that's what this R would be. Here's the lowest point, and that would be the highest. And there's the lowest, there's the highest, and so on. And those are the R values. So this is showing over a short period of time a machine made parts that varied this much in a dimension. And as long as you're doing this both in the long-term and the short-term basis, you're going to have a consistent R chart. So again, this represents the average of the numbers within a subgroup. That's how it represents those 4 numbers. And this represents the range from the minimum to the maximum data item.
Okay, and then we have another one. This attendee wants to know if there are any free Excel templates that you would recommend.
Free Excel templates.
I'll have to ask for some clarification on that. I'm not quite sure. I was hoping you would understand what he was referring to.
I believe it's Quality Expert. They're not free. Is based on Excel. And it's something I run into periodically out in the field. I happen to work with more commercial SPC software, but I'm pretty sure it's Quality Expert's the one that's Excel, and I can tell you they do an excellent job. It's not as versatile as a higher price commercial product, but it covers quite a range of needs, not just X-bar and control charts, quite a bit more.
Okay. We have another attendee just asked, he says he has students that are working on their NIMS credentialing, the National Institute of Metalworking Skills.
Sure.
It says one exercise the students need to learn about is, SPC, and it's just asking for, what are some recommendations you might have for ways to teach students about SPC?
The internet is just flooded with information. Unfortunately, I don't know of anything where they do things like the control charts for you for free. So if you're going to do a control chart and you work with a subgroup size 3, 4, 5, something like that, do all of 4 or 5 points in a row just to see how it works. After that, it just becomes a laborious exercise in calculations. And you may even find somebody that will have an online system that will let you try it for 30 days for free or something like that. The mathematics is not hard, but it's very labor intensive. So your internet's going to be your resource there. It's going to either be cheap or, if nothing else, it'll at least tell you how to do it yourself. But you being the operator of the machine, you want to be more familiar with what X-bar charts look like than how to necessarily manufacture them yourself.
Okay. And another attendee wants you to explain what the concept of standard deviation.
Okay. When we have variation that occurs, there's an average, which would be roughly here in this data. And so how much does this data point move from there, and this data point move from there, and this one's really close, but that one's further away. So the standard deviation of this is the average of how that data moves away from the center of where that data would be. It's in a statistical system, you have average. What do all the numbers add up to and calculate out to? And you have, in this case, it's R bar, which can be used as a substitute for standard deviation, which is how much variation does my data see when I look at it over the whole summation. It's a pain in the neck to calculate by hand. Electronic calculators make it easier. I'm sure you'll find things on the internet that will do standard deviation calculations for you. And just think of it as the average spread. How much does well, actually I should use this one. How much does the data spread from here to where? Roughly halfway up here. And that would be roughly the standard deviation here. This total distance from here to this dotted line is 3 standard deviations away. And this is on the X-bar R chart. Even though the R chart's down here, here's where you could see what your 3 standard deviations is by subtracting this number from that number and dividing by 3. And again, that represents how much variation your data is seeing.
Okay, well, I am not going to jump the gun again, so I'm going to give it another 30 seconds in case somebody is furiously typing a question into the question pane. I don't see anything else. All right, I think that is it. Thank you so much, Bob, for the helpful presentation.
Yeah, thank you guys for tuning in to see this. I appreciate it.
Certainly, this has been terrific. So, on behalf of Modern Machine Shop and Mitutoyo America, thank everybody for coming, and enjoy the rest of your afternoon.